Um, Hi. I'm going to be talking about some of the work that we've done at Feral on porting to Vulkan. So we're Feral Interactive. We're a Mac, Linux, mobile games publisher. Primary focus is sort of in-house ports of games. So we've released over 100 Mac ports so far. Then about 5 years ago, we started doing Linux as well. And then in the last couple of years, we've also started doing mobile ports. So I'm Alex. I'm primarily a Linux developer. And then over the last year and a half, I've sort of led the development of the Vulkan support in our ports. So far we've done 4 releases with Vulkan support on Linux, you can see here. So the first of these was Mad Max. So we originally released Mad Max using OpenGL back in October 2016. And then in March last year, we released a beta update with Vulkan support. And if anybody was here last year, we did a talk then about the work we did on that beta release. So then after that, June last year, we released Dawn of War 3. This shipped with both OpenGL and Vulkan support. It was OpenGL by default, but we also had Vulkan in there as a sort of experimental option. Then in November last year, we released F1 2017, and this was the first game that we did that was Vulkan exclusive. And then finally last month, we released Rise of the Tomb Raider, also Vulkan exclusive. So those first 2 beta releases, Mad Max and Dawn of War 3 that we did, weren't sort of really production quality. So they had sort of several shortcomings that are in the Vulkan path that we knew about, that we knew we needed to resolve before we moved over to using Vulkan by default. So one of the main aims of having these beta releases was to collect feedback from users. So we set up an email address where users could email directly to us in the development team to report any issues that they had. And the things we had reported range from just things like the drivers not being configured properly to actual issues with specific hardware, specific system configurations that we'd not picked up on during our internal testing. So having this early feedback was a big help for us to try and avoid having these sorts of issues down the line when we actually did start releasing games that were Vulkan only. And then over time, we've made many improvements to how we're using Vulkan since these initial releases. So I'm just going to be talking about some of the examples of the problems that we found and improvements that we've made over time. So the biggest area that we knew we needed to improve on over the beta releases was with our memory management. So specifically, we had some problems with not really handling overcommitting VRAM very well. And also had some problems with fragmentation of memory, which could lead to our memory usage being higher than it needed to be over time. So overcommitting VRAM, this is basically when the amount of memory that you need for all of your resources is greater than what can actually fit in the VRAM that you have available on the GPU. So it can happen, for example, if you've got a user trying to play the game on high graphic settings, but with a low VRAM GPU. So if a user does try to do this, we don't really want to sort of give up and crash, because we can make it work, we can still make it perform reasonably well. However, I will say that we try to do this sort of within reason, because it's like for instance, if a user is trying to run, say, 4K resolution and then maximum graphic settings on a 2 GB GPU, then that's probably not really going to work very well no matter what we do. So that's where we kind of draw the line at trying to make it work well. So with Vulkan, this is not something the driver will handle for you, unlike D3D11, GL. So when you, at least on Linux, AMD, NVIDIA, Intel desktop drivers at least, this may be different on other platforms, but when you exhaust the available space in a heap, then a VK allocate memory call on it will fail, return VK error out of device memory. So you have to go and handle this. So for example, if you were trying to allocate from device local, fall back onto a host heap. But doing this naively is something that can cause you performance problems. So we found, we had an example of this with the Dawn of War 3 beta release, which I'll show you now. So this was a benchmark that was published by Phoronix shortly after we released the game. And it's a performance comparison between the OpenGL and Vulkan paths running at 1080p high graphics preset. So you can see on the top and bottom cards, then we've got very close performance between GL and Vulkan. That's 780 Ti, not GTX 970. But then on the middle two, GTX 950 and 960, we've got on the Vulkan path the performance just completely fallen off a cliff here. So we saw these benchmarks published, and we were sort of like, well, what's gone wrong here? So we started investigating what happened here. And the root of the problem is that, so the top and bottom cards, like 3 GB, 4 GB VRAM, whereas the middle two, the problematic ones, are only 2 GB. So how did this happen? So Dawn of War 3 loads all of its textures and other resources on a loading screen when you're loading into a level, in this case the benchmark, before the game has even started rendering at all. Then only after the loading is complete does it go and allocate render targets, storage buffers, etc., once it's actually starting to render the game. So on those 2 GB GPUs, if you got the texture graphics, texture quality settings set high like we had on that benchmark, then the textures end up using most, if not all, of the VRAM. So the original behavior we had in those beta releases was if we get device local memory allocation failure, then just regardless of what we're trying to allocate, just fall back onto the host memory heap instead. And yeah, funnily enough, this is really, really bad for performance, so don't do that. So the solution to this was that we changed up our memory manager so that it requires that we place render targets, GPU writable buffers into VRAM. So if we fail to allocate one, then we go through this sort of procedure that tries to make some space available. So first thing it will try and do is defragment all of the resources that we currently have allocated, and I'll describe that more in a bit. And then if that doesn't make enough space, then it will go and move out other existing resources in device local into the host heap instead. And that gets done in least recently used first order. So yeah, doing this brought the performance we were seeing in Dawn of War 3 on Vulkan in line with what we had on GL when we were in VRAM constrained situations like that benchmark. So one thing we did find while we were implementing, testing all of this, implementing this stuff, was it was useful to have a way for us to simulate having less VRAM available, just so we didn't have to go and physically swap out a GPU to go and test the behavior on different amounts of VRAM. So this, we added two sort of types of limit we could set. First thing we had was just a heap size limit, which is basically behaves as though the VK physical device memory properties returned by the driver is actually returning a lower size than the real heap size limit, because we have a few places where we're doing things, making decisions based on the reported heap sizes. So having that limit just tests the behavior of those decisions that get made based on that. And then the second thing we did was this sort of early failure limit, which makes it behave as though VK allocate memory fails when the amount of memory that you've actually allocated from a heap is less than the total reported heap size by the driver, because that is what will actually happen in the real world usage, because you're not the only one that's using VRAM. You've got other usage by the operating system, other apps running, and then there's also some amount that's going to be used by the driver internally as well, because things like descriptor pools, command pools, they might take up VRAM as well. So having that limit just tests that we're actually responding to these failures properly. So yeah, the next problem we had with memory management was fragmentation. So what our memory manager does is it allocates large pools of memory from the driver and then sub-allocates out of these to individual resources internally. And this is sort of generally what you should do on Vulkan. You'll hear more about that later on from the memory management talk. But we found over time we were getting these pools could become fragmented. So for example, Rise of the Tomb Raider, it's sort of like a semi-open world game, very few loading screens during gameplay, and it's just constantly streaming resources in and out as you move around the game. So over time, because of doing all this streaming, we can end up with memory fragmentation, resources spread across a number of pools with gaps in between them that aren't being used. So as a result of this, our memory usage can become higher than it actually needs to be. Because we have, even though the total size of all of the individual resources that we have is lower, there's a bunch of free space within the pools that we have that's not being used, but we've still allocated. And yeah, we can't free any memory pools back to the driver while even just like a few resources are in them. So for example, we allocate texture pools of 128 megabytes, but even if we've only got like 2-3 textures in there, then we still can't free that, and the rest is just sort of not being used. So yeah, quick example of that here. This is in Rise of the Tomb Raider. Now this is the sort of debug tool we wrote that shows the current state of the memory manager. And it's got a simple visualization of the layout of the resources within each memory pool. So you can see here the expanded section is the texture pools. Each of those is 128 megabytes. And the blue space there is used space, and the green space is free space. So this is the state of things. We've just started the game here and loaded a save directly into this point in the game. So it's like just after loading. So everything to get to this point has been loaded all together. And so everything's nice and compacted together in the memory pools. But then if we go and play further on from this point, further on through the game, we get to here. It's a bit dark, you can't really see what's going on there, but basically what's happened is we've gone from the level we were in on the previous slide was one of the big sort of hub areas of the game, the Soviet installation, which is like one of the largest areas of the game. And then what we've done is gone through to this much smaller sort of linear section. So there's, as we've come up to this point, the game sort of streamed in some of the resources for this new level. And some of the resources like are shared between this area and the previous area, but some from the previous area are no longer needed. So once we've got into this point, then the game has gone and freed a bunch of resources, and it's left all of these gaps throughout the memory pools. So if you actually look above, might not be able to read that, but if you see the usage statistics above that, it says there's only 63% of the memory that we've allocated is actually being used for resources there. So the solution we had to this was implement a memory defragger. So basically this just tries to move resources around so it compacts them into as few pools as it possibly can, and then frees any memory pools which become empty as a result. So in F1 2017, the first game we shipped this in, we had it just as something that gets done at sort of fixed points on loading screens at the start and end of a race. And that, because it's being done on a loading screen, the performance of it there doesn't really matter that much. So it just goes and defragments everything that's currently allocated, all resources. And that can take like a few hundred milliseconds. But yeah, because it's on the loading screen, that's not really much of an issue to cause like that kind of stutter. But then Rise of the Tomb Raider, as I said before, it's a semi-open world game, rarely any loading screens, and it's just streaming all the time. So we have no opportunity to go and do this like stall for 100 milliseconds, defragment everything, because if the user will notice that happening. So for that, we went and implemented the ability to do defragmentation in the background as well. And this basically just tries to keep the amount of memory that we're actually using for resources versus the total size of the pools that we have allocated above a threshold, so that at any given time we're not really holding on to too much more memory than we actually need to. And then this is rate limited to avoid having too much of an impact on the performance of the game, so it's done just like move a certain amount, like small amounts over time. So yeah, going back to that example, that was what we had before. This is actually without the memory defrag systems enabled. But then if we do this, this is now from doing the same thing. So we've done the exact same sequence of events here, loaded into that previous point, and then played forward to this point. But now we've got memory defrag enabled, and you can see there that we've actually got, like, everything is now much more compacted together. And then if you compare, you see there's actually 2 less memory pools allocated, so each of those is 128 megabytes. that means we've reduced our memory usage there by 256 megabytes. So yeah, just having this memory defrag system has basically been really useful for us to try and keep the VRAM usage of the game under control. And not just VRAM usage as well, because if we've fallen back to like the host heap for certain resources, then we're using system memory as well. So we need to defrag any pools that we have in the host heap as well, so it keeps system memory usage under control as well. So the next thing we made improvements on over what we were initially doing was how we managed descriptor sets. So the initial implementation that we did was just rewriting descriptor sets per draw every frame. And yeah, we just had a bunch of per frame descriptor pools, and we reset the entire descriptor pool with VK reset descriptor pool once the previous frame that it was used in has completed. So this was something that worked pretty well on the desktop drivers, though we did think that we might be able to do something a bit better. But what really motivated us to go and change what we were doing was that it's sort of very costly on some mobile implementations. In particular, ARM Mali GPUs don't particularly like this. So we've noticed on, because we've noticed on our mobile game, we're currently working on a port of Grid Autosports to Vulkan Android. We noticed that on that we were getting quite significantly lower performance on ARM GPUs compared to other phones with similar specifications, and the cause of that turned out to be how we were managing descriptor sets. So the new strategy that we have is that we now have persistent descriptor sets, and we just generate and cache these as needed. So the games that we've currently ported to Vulkan have all been sort of like D3D11 style engines. So they have like the D3D style binding model of just slots that you arbitrarily bind resources to, swap them out as needed. So every draw we take the resources that the shader needs, put them into a key, look up based on that. If we find an existing set, use that. Otherwise, create a new one and store it to be used later. And then on top of that, we're now using the dynamic uniform storage buffer descriptor types. Because this works well with how we implement buffers for like frequently updated buffers. So we do them as a sort of ring buffer, where every time we want to write new data to the buffer, just advance an offset in the buffer and write the new data there. So at bind time, we have to go and add on the offset to the latest data in the buffer. So if we were using the non-dynamic descriptor types for that, we would have to have a different descriptor set for each offset that we want to bind. And yeah, changing the offset can happen many times per frame, so we could end up with lots and lots of descriptor sets being generated because of that. So instead, we're just using dynamic descriptor types. And this just means that we change the offset by rebinding a descriptor set with a different offset. So yeah, compared to the original implementation that we had, rewriting descriptors per frame, on desktop gave sort of like a modest performance improvement. So for example, Rise of the Tomb Raider's benchmark, depending on driver, it was like 5% improvement. But then, as I said before, our Mali GPUs, it was quite bad before. This gave us around about 30% performance improvement. And that brought our performance on those GPUs in line with what we were seeing on other similar spec mobile GPUs. So with this descriptor pools, we have a bunch of global descriptor pools, and then we create these as needed when we find that existing pools are empty. So one thing we found with this is that we could end up with quite a large number of descriptor pools allocated, and these can have a VRAM cost. So the Vulkan API doesn't provide you any way to check the memory usage of objects like descriptor pools. But if you've got like driver source available, so for example on AMD, you can actually go into the driver and just sort of see what it's allocating for a descriptor pool, compare that with the number of descriptor pools you have, their sizes, and then work out sort of like roughly how much memory you're using for these. So we did this, looked into this in Rise of the Tomb Raider, found out we could reach around about like 50 meg peak VRAM usage for descriptor pools. which is sort of getting a bit high, so we looked into seeing if we could reduce this a bit. So we just made it so that we periodically clean up old descriptor sets, which we haven't used in a while. And then doing that brought the peak usage we could have for descriptor pools down to around about 20 megabytes, which is quite a bit better. So a caveat with how we're managing descriptor sets now is like by having global pools and then freeing individual descriptor sets, is that we can end up with descriptor pool fragmentation. So when this happens, the allocations from this descriptor pools can occasionally fail when the number of descriptors you've used is actually less than the total size you specified when creating the pool. So in practice, we've not really found this to be too much of a problem. It does happen. When it happens, we just sort of handle it by trying to use a different descriptor pool. And we've not really found that to be having too much of an impact on the performance or just like increasing the number of pools we have, because eventually with this sort of periodic cleanup of old descriptor sets, it sorts itself out over time. But you just kind of need to be aware that this can actually happen, and you need to handle it. So next thing I'll talk about is threading. So yeah, Vulkan gives you much greater opportunity for multi-threading compared to the older APIs. There's very few places where the API is going to say you have to do all of this from a single thread, like you have a device context or something you have to use on a single thread, like the older APIs. So we're using it as part of doing resource creation and as part of our main rendering. So I'll give you a few examples of what we're doing here. First thing, pipeline creation. So on Vulkan, unless you have very few pipeline states, it's generally best to create these ahead of time rather than like doing it as needed at draw time based on current state. Because if you do this, pipeline creation can take a long time. It's like got to compile the shaders. And if you do this at draw time, then you can cause quite a bit of stuttering, particularly if you have a lot of like shader variants, pipeline states, things like that. And yeah, the API lets you create pipelines on multiple threads simultaneously. So in our previous OpenGL releases, we've often had to have loading screens to go on pre-warm shaders. So the driver isn't having to compile them at draw time based on the state at the first time it needs one. And these loading screens can end up being pretty long, like if you've got a large number of shaders. So the worst example of this was the port we did of Deus Ex Mankind Divided. And we had a loading screen at startup to pre-warm shaders, and this could actually take like 5 minutes or more when the driver cache is clear. So in Rise of the Tomb Raider, it has a lot of pipeline states, like tens of thousands. And because, as I've said before, it doesn't really have many loading screens during gameplay, we can't really go and create these on a per level basis on loading screens or anything. And also the number of pipelines is just too many to go and pre-create them at startup within a reasonable amount of time on a loading screen. So we really wanted to try and avoid doing that if we could. And I will note that you do have like the VK pipeline cache API, which lets you get a pipeline cache and then save it out to disk. And then also on desktop, some of the drivers, so NVIDIA, and I think AMD's does as well, have sort of driver managed on disk cache, which will help performance like when you do actually have the pipelines cached. But we still have to care about the user experience on the first run of a game, and also if the user changes their hardware or the driver, that will invalidate what's cached as well. So we have to care about what happens in those situations. So sort of the solution we had was use multiple threads for doing pipeline creation. So first thing we do is we do have in Rise of the Tomb Raider, there is a loading screen when you first load the game. So you start the game, load into a save, and then you get a loading screen there. So on that loading screen, what we do is that we use all but one of the cores that are available in the machine to create pipelines for the specific game area that we're loading into. And yeah, we found that on the desktop drivers at least, the pipeline creation just generally scales very well. The more cores that you use for it, obviously up to the number of cores in the machine. So on this loading screen, it makes sense for us to go and use most of what is available, leaving as one core spare to do like the rest of the loading for the game, to try and speed things up. But once that initial load screen is complete, then there's rarely any loading screens after that. So what we do for that is use a single background thread to go and continue creating pipelines for the surrounding areas from where you currently are in the game. And then the priority of that thread is set lower to try and reduce the performance impact that it's having on the rest of the game. So on machines that do have enough cores available, like say more than 4, then it doesn't really have any impact at all on the performance of the game, doing this pipeline creation on another thread. With fewer cores, so with 4 cores, it sort of does have a sort of small performance impact. Less than that, you do get quite a noticeable impact from having this other thread running. But it's not something that goes on forever. The pipeline creation does get finished eventually. So we decided that like having this like period of lower performance would be preferable to having to make users sit around on a loading screen waiting for it to complete, where they can't do anything, they can't play the game at all. So going back to that initial loading screen, in many cases we find that the pipeline creation completes within the time that it takes us for us to load everything else for an area. So it's very rare, except for like on the biggest hub levels in the game, it's very rare that we end up on a loading screen waiting exclusively for pipeline creation to complete. So that's something I was like quite happy that we managed to get done, because having these really long loading screens where you're waiting for shaders to compile isn't a particularly nice thing for users, and for us especially if it's something that doesn't happen on the original Windows D3D version of the game. And yeah, this wouldn't have really have been possible for us to do with OpenGL, because unlike on Vulkan, we don't have explicit control of pipeline creation. It's just the driver compiling shader variants at draw time. So we can't really easily offload that to another thread and like do it in the background like this. So final thing to talk about is how we're threading things during our rendering. So I said before, current ports have been D3D11 style engines, so their graphics API usage is mostly off a single thread. So internally in our Vulkan layer, we have to do a bunch of work every draw or dispatch. So as I said, look up or create a descriptor set, find a pipeline to use, and then we also have this resource usage tracking, because we automatically track resource usage and use that to automatically add barriers. So if you look there, that's just like profiler example output that's just got the blue blocks are work in our Vulkan layer, green blocks work in the driver, and then there's gaps in between where this is on the game's rendering thread in Rise of the Tomb Raider. It's just other logic that's happening on that thread. So we'd often find that we ended up bottlenecked on the rendering thread during some intensive scenes. So to try and improve that, we implemented an option that basically just offloads all of the work that we're doing in our Vulkan layer onto a worker thread. So graphics API calls by the game's rendering thread just write commands into a queue, and these get consumed asynchronously by a worker thread, and that goes and does all the heavy lifting for each draw. So what that effectively means is that we're now doing the work in the Vulkan layer in parallel with all of the rest of the rendering logic on the game's rendering thread. So you can see there that's now like the yellow blocks are the calls from the game's rendering thread, and they're just queuing the commands, and they're taking much less time, so we can now do all of that in parallel with the work that we're doing. So on top of that, we also implemented another option that can also offload all the VK command recording calls into the driver off from that main worker thread onto another worker thread. Because we were measuring that we were finding like quite a bit of CPU time on our worker thread being spent in the driver. So we thought we might be able to get a further improvement by trying to offload this onto another thread. So that's what you get with that, is now we've got our work, driver work, and game rendering work all being done in parallel. So for Rise of the Tomb Raider, we ended up enabling this only for machines that have 6 or more hardware threads. And in that case, we were finding we could get around up to about 10% performance improvement in some tests. But with fewer hardware threads available, then this actually ends up hurting performance slightly, because now having all of these threads is competing for CPU time with other threads. We haven't got enough cores to run everything in parallel, because on top of these 3 threads there, we've also got other game logic, things like that going on. So just quick performance comparison between these threading options. These are these average frame rates measured at 2 sort of like fixed viewpoints in some CPU-intensive locations in the game. So there's Soviet installation and geothermal valley, which are the 2 sort of biggest hub areas. And this is on AMD Vega 56 Core i7 high graphics preset. So for both of these locations, having the main worker thread, this gives us around about 50% performance improvement over no threading. Then on top of that, if we enable the driver command thread as well for geothermal valley, it gives another 6%, and then Soviet installation another 10% over that. And for both of these cases, we've gone from being completely CPU bound on this hardware to now entirely GPU bound. So yeah, we get a big performance benefit just from this sort of fairly basic threading model. And as I said before, Vulkan gives you a lot of flexibility with regard to multi-threading. So in future, we could probably actually go quite a bit further than this and try and scale the work that we're doing in our Vulkan layer over multiple cores, the more that are available. And yeah, to finish off, I'll say Vulkan has been a fairly good experience for us so far. So on desktop, at least, the drivers are pretty reliable by now. So every release that we do, we do tend to find like a few issues with the drivers, but generally it's nothing sort of major broken. On Linux, where we're mainly targeting, we have several open source drivers available. So there's the Mesa drivers for AMD and Intel. That's Intel's official driver, and then also unofficial AMD driver. But also AMD open sourced their official driver, I think, at the end of last year, which is the same as their proprietary driver except for the shader compiler. So having these open source drivers, we find, is a huge help to us, both being able to debug issues, because we can go into the driver and see what the driver is doing when we suspect the driver might be at fault. But also it's just useful for understanding how the driver is behaving, which is helpful for optimization, because we can go and see like the exact sort of performance implications of what we're doing. And then the tools ecosystem is sort of just continually improving. So tools like validation layers, RenderDoc, etc. They're generally making the API easier to work with. So the current state of things is much better than when we first started working with Vulkan, and it's generally pretty nice to work with these days. So on our side, we're continually improving our Vulkan support, gets better with every release, as we learn more about the API, as the API itself improves. We've shipped 2 Vulkan-only releases on Linux so far, and for the most part, we expect to be targeting Vulkan for Linux releases going forward as well. And then finally, we're planning to release our first Android title, Grid Autosport, later this year, and that's going to be targeting Vulkan as well. So that's all I have. Does anybody have any questions? Yep.
So the work you did on memory defragmentation seemed like something that a lot of vendors are going to have to do. Is it something that's open source or open sourceable, or other implementations that need?
There is AMD's Vulkan memory allocated library. I think you'll hear about that in the next talk as well. That's an open source library, and I think that does have a defragmentation implementation in that.
How long did it take you to get your first Vulkan render up and running when you started working on it?
It was actually only from the point of starting, it was only about a month, I think, to get from the point of first starting to the point where it was sort of basically running. I mean, at that point, it was still like rendering issues and the like, performance problems, etc. So, but from that, it was like we released Mad Max in about, I think it was March last year, and we started doing that back in November the year before. So that was about 5 months to get to that point where it was actually sort of shippable in beta quality. Yep.
We found that sphere B blob size is a major problem for
Sphere V size. Not particularly. I mean, we're generating all of our shaders. So our shaders are generated runtime, which is something I'd like to improve on. But we're compiling to Sphere V at runtime. So we're not saving that on disk or anything. But yeah, there is Rise of the Tomb Raider, it's got lots of shaders. We did find we had some issues with memory usage on that, and one of the things that did contribute to that was having all of these Sphere V blobs in memory at once. So it would be useful to try and cut that down.
Are you translating from DXBC?
Yes. Yeah. Yep.
But just going a little further on the question, so you say you generate Sphere V at runtime. Do you run it through things like Sphere V opt?
No, I have investigated that. Found that Sphere V opt it currently takes quite a long time to run. So doing that at runtime is just it's not possible. I did for GLSL. I didn't really find that it was giving us much. Because we're translating from DXBC, we've already had all the optimizations that FXC has done on it. So we didn't really measure any benefit from doing that, and it was just taking quite a long time to run. But that was quite a while ago. I've not tried within the last 6 months at least.
On that as well, I think Google submitted their changes to optimize DXC compilation, Sphere V compilation, HL.
Yes, yeah. Yeah, shader compilation is definitely something I want to try and look into improving. Yeah.
So I was just curious, what's the most limiting feature or limiting aspect of the API or feature that's missing, or basically that you're paying back in?
Sorry, can you say that again?
What's the main limitation of the API or missing feature that's currently restricting you from using it as your primary backend?
We are using it as our primary backend now. For our latest 2 releases, we've switched over to that. We're not targeting Windows. We're specifically doing the Linux ports.
There's nothing really missing from the
For our current games, we do have some stuff in early development we're finding some missing features, but we're just sort of going to try and push for new features where we find that we need them. Yep.
You mentioned at the end that you are targeting Android Vulkan on
Yeah.
the very last title. How have you found the process from developing Vulkan on Linux to transition to mobile?
A lot of the work does carry over, but there is some things that are different. So, for example, memory management is one of the biggest things I can think of. Is that there's difference in the memory architecture between the mobile GPUs, desktop GPUs, and you have to make sure you're considering all of these things, and make sure that your implementation actually handles the differences between these different architectures. But for a lot of it, it's the same code path. It's mostly shared. We just do some specific tweaks for each platform where we find that we need to. Anyone? Yeah. Yeah, we're just about out of time. Right. Thanks.
Thank you.